Welcome to this explainer. Today, we're looking at a hidden language that dictates literally everything we build, material selection. It's basically a massive matchmaking process where engineers have to pair a specific material with an exact set of physical demands. Get it right, and we conquer the skies. Get it wrong? Well, things literally fall apart.
Okay, let's dive into this. Take a modern jet engine. This isn't just a hunk of metal. It is a carefully orchestrated symphony of highly specific materials. Building a machine like this, which operates under mind-boggling temperatures and immense physical stress, relies entirely on selecting materials with the exact right properties for survival. If the metals inside this engine can't take the heat, or if they deform under those massive rotational forces, the results are absolutely catastrophic.
So, here is our roadmap for today. We'll start with Section 1, the design engineer's dilemma. Then Section 2, the shapeshifters. Section 3, resisting forces and shocks. Section 4, failure points and machinability. And finally, Section 5, real-world engineering materials. We're going to break all of this down step by step. Let's kick things off with Section 1, the design engineer's dilemma. Finding the quote-unquote best material is rarely just about finding the strongest one. It's actually a constant, high-stakes balancing act between physics and economics. Think about it. You might design the most perfect alloy ever conceived, but if you can't actually source it and get it to the manufacturer, it's completely useless. Then there's suitability. Will it actually survive the everyday working conditions out there in the real world? And of course, there's the cost. Engineering is an economic discipline at its core, meaning your chosen material has to achieve the goal at the absolute minimum price.
To really understand how suitability dictates our choices, just look at this massive clash of physical properties between tungsten and tin. Tungsten is incredibly dense and has a staggering melting point of 3410 degrees Celsius. Tin, on the other hand, it melts at just 232 degrees. If you're designing the filament of a light bulb, you desperately need a material like tungsten that can withstand massive heat without deforming. Try building that with tin, and you would literally just end up with metallic puddle the second you flip the switch.
Moving right along to Section 2, the shapeshifters.
Two of the most fascinating mechanical properties are elasticity and plasticity, and they act as complete opposites. Elasticity is the ability to snap right back to an original shape after a deforming force is removed. And get this, it's a surprising quirk of physics, but steel is actually more elastic than rubber. No way, right? Well, on the flip side is plasticity, where a material permanently retains its new shape after being deformed under a load. If you're stamping a face onto a metal coin, you need the material to be highly plastic so it holds that image forever without springing back into a flat disc. Now, what's really interesting about this slide is how easy it is to confuse ductility and malleability, but they involve very different mechanics. Ductility is a material's ability to be drawn out into a wire using a pulling or tensile force. To pull this off, a material like copper or mild steel has to be both strong and plastic. Malleability, however, is a special case of ductility that allows a material to be rolled or hammered into incredibly thin sheets. For this, like with lead, for example, the material needs to be highly plastic, but it actually doesn't need to be exceptionally strong. All right, on to Section 3, resisting forces and shocks. So, when an external force attacks a material, the internal resistance that pushes back is called stress. Strength is simply the material's capacity to generate enough internal stress to fight off that outside force without yielding or breaking. The greater the strength, the more forcefully the internal structure can resist the outside world. It's like an invisible shield holding everything together. When those external forces strike suddenly, it becomes a battle of toughness versus brittleness. Toughness is how well a material can absorb a violent impact, like a sudden hammer blow, without fracturing. And interestingly enough, toughness actually drops when a material heats up. Contrast that with brittleness, which is the exact opposite of being ductile. Brittle materials like cast iron don't stretch or distort gracefully under pressure. They just suddenly and violently snap.
Then we have the incredibly dynamic property of resilience. When you compress a coiled spring, you're witnessing resilience in action. It takes a shock load, absorbs that energy per unit volume right into its internal structure, stores it safely within its elastic limit, and then powerfully bounces back.
Let's move to Section 4, failure points and machinability.
Because, let's face it, no material is invincible. Eventually, physics always wins. Before any metal goes into a bridge or a car, it is ruthlessly tested to destruction in mechanical testing machines, just like the one you see here. Engineers apply immense pressure, pulling and crushing materials to discover their ultimate breaking points. We have to know exactly where those failure limits are, so we can design safely within the margins.
And this brilliantly illustrates a really insidious issue: fatigue. Fatigue doesn't announce itself with a giant hammer blow. It's a progressive, silent killer. First, the material faces repeated cyclic stresses that are actually well below its yield point, so everything seems perfectly fine on the outside. But deep down within the structure, fine, microscopic cracks are progressively forming. The final step is a sudden, totally unexpected failure. If you are designing spinning shafts or engine connecting rods, fatigue is your absolute worst enemy.
Then there is creep. Creep is a slow, permanent deformation that happens when a material faces constant stress at high temperatures over a long period. The material literally, creeps out of its intended shape. This is a life-or-death factor when designing internal combustion engines, boilers, or those gas turbines we talked about earlier. The extreme heat, combined with constant rotational stress, means engineers must choose materials highly resistant to creep.
But before we even worry about fatigue or creep in the field, we have to actually build the part. And that brings in machinability. This is simply how easily a material can be cut and shaped. You could have the strongest, most resilient metal on Earth, but if it requires too much energy or completely destroys your cutting tools to shape it, it's pretty much useless. Brass, for instance, is far easier to machine than steel, making it a highly practical choice in the design engineer's dilemma.
Which brings us to our final stop, Section 5, Real-World Engineering Materials. In the world of metals, we essentially split the family tree right in two. On one side, we have ferrous metals, which contain iron as their main constituent. Think of materials like cast iron, wrought iron, and steel. Ferrum is actually the Latin word for iron. And on the other side, we have non-ferrous metals, which use a base other than iron. A perfect example is the highly ductile non-ferrous copper woven into those electrical cables.
Of course, not everything is metal. Non-metallic materials, particularly plastics, are highly prized for their low density, their cost-effectiveness, and their flexibility. But chemical properties still dictate their fate. A plastic chair, for instance, could be made of a thermoplastic, meaning it can be softened by heat and continually remolded. Or it could be a thermosetting plastic like Bakelite. These undergo a permanent chemical change under heat and pressure, resulting in a rock-hard product. Once it sets, it's set for life. There's no going back.
Which brings us to the end of our explainer. But before we go, I want to leave you with a bit of a challenge. Look around you right now. Look at your computer, the chair you're sitting on, the structural beams of the building you are inside. They aren't just static objects anymore, are they? What invisible mechanical properties are currently working in secret to hold your room together? Visualize the stress fighting back against gravity in the structural beams. Where is elasticity actively at work? Where was machinability required to shape the joints? You now have the eyes of a design engineer. I promise, you will never look at the physical world the same way